Speaker of the day today is Ravi Kumar from Google Research. So Ravi has been a pioneer in not only in algorithm design and theoretical computer science, but in a large range of areas over the last 20 plus years. He has worked on data mining, web search, data streaming, and really uh, it's really a very long list of areas that he has worked on and made substantial contributions to over a long period of time. So we are very glad to have Ravi speaking today from California. And of late, he has been working on, and he has been one of the sort of people who have been uh, leading the effort to incorporate information from machine learning algorithms or machine learning tools into algorithm design and trying to make use information we know from learning nowadays to state-of-the-art algorithms, particularly in augmented research. And that's what he's going to be talking to us about today. Over to you, Ravi.
Thank you so much. Thanks, Dirmalia, for the nice introduction, and good to see you all. I hope you're enjoying Chennai. Actually, I'm from Chennai. That's where I was born. So it's a great city. I'm sorry I couldn't be there in person due to various reasons, but next time I'm sure I'll be there. So I'm going to talk about today about some topic that's been close to my heart for the last 3-4 years. It's learning augmented algorithms. I'm going to address a very specific aspect of this, and it'll be clear as the talk progresses. And I'm going to cover some work that I have done with a bunch of my co-authors and peers, like Aditya from Utah, Ashok from Boston, and Sangjin from Merced, and another Aditya from Merced is a student, and Manish, my colleague at Google. So by the way, I'm in the Google office in Mountain View, California. Okay, I'm sure you know most of these concepts well by now, but nevertheless, I just want to set the stage for a clear picture of what I'm going to talk about next. So, what the topic of interest today is online algorithms. So, this is a classic formulation with the aim of how to make decisions under uncertainty. So, in a very typical setting, the inputs arrive one by one. The algorithm, denoted by the yellow arrow, consumes these inputs in an online fashion. And every time it consumes one input, it's supposed to make a decision that it cannot undo. Okay. So that's the whole setup here of online algorithms. And this is quite common. It can capture many forms of uncertainties and unknown things about the future. And in particular, there are two paradigms to handle the unknown aspect. The first is something that most TCS folks are familiar with, which is online algorithm. So the way online algorithms are set up is that they assume the future is fully unknown. In fact, in the typical algorithm style design, they assume the worst possible future. The inputs in the future can be adversarial, and you want to design an algorithm that can hedge against any possible malicious or adversarial kinds of inputs. And therefore, this pessimistic way of looking at the future makes it very hard to exploit interesting patterns that can occur in data. For example, if the data in a particular setting satisfies some nice properties or comes from even some known source, it's hard to algorithmically exploit that without compromising something else. So that's one of the aspects of online algorithms. But of course, there have been many models that try to overcome this particular handicap. We won't go into those details, but this is something to keep in mind. And online algorithms have been studied for many combinatorial settings like caching, scheduling, online optimization like set cover and other kinds of problems. That's like one side of the story. The other side is like given by machine learning, which almost operates in a dual fashion. Right? Machine learning assumes that the future is not that uncertain. In fact, most machine learning models try to exploit the history or what it has seen before to build some models. And these models can be used to predict what's going to happen in the future. So given this way of operating, they tend to be excellent in terms of performance when it comes to normal inputs. In fact, they have very good on average performance. However, unless one is really careful, they can be easily fooled by outliers. In fact, sub area of machine learning, something called robust machine learning, deals with this particular problem. Most ML models tend to be less robust to outliers. You can easily make an ML model fail by just manipulating like one or few points. And the typical kinds of predictions that ML models engage are what is the next page that's going to arrive, or in scheduling settings like how long is the job going to run, and so on. So that's the other side. So we have two paradigms, online algorithms and machine learning, and both of them handle the unknown aspect of the future in slightly different ways. Um, Next, we look at what are the online performance metrics. These are studied in these two domains. One is the competitive ratio, which happens in the online algorithm setting. There, the performance of an algorithm is measured against an offline adversary, offline algorithm. An offline algorithm knows the complete history of what's going to happen, arrive in the future. So it knows it's omniscient. So it knows the complete future. So it can therefore make decisions that are optimal. And this comparative ratio tends to be like a multiplicative quantity because it's studied as a ratio of the performance of the algorithm to the performance of the optimum offline algorithm, maximized over all instances. And this notion is used in combinatorial settings. In machine learning, there's another notion, slightly different notion used called regret, where regret it measures the performance of an algorithm against a class of benchmarks. And it again tends to be like an additive quantity as opposed to a multiplicative quantity. And if you know a little bit more machine learning, this is similar to like excess risk. You're looking at the expected loss of a function f compared against the minimum loss of any function g from a specified class, the script f. Like that's the benchmark class. And you take the difference between these two, and that is a quantity that shows how well like my algorithm works in this online setting. So we'll look at both these measures. And that's why I'm introducing them here. Okay. So now that we have the framework set up, what is the high level goal of learning augmented algorithm? So the question that we ask here is, can one improve the performance of online algorithms when there is some information about the future that could be possibly wrong? So again, you have this online setting, and now you have a hint or a prediction or advice, whatever you want to call it, available to the algorithm at that time or before the time it's going to make this irrevocable decision. And the question is, if this such a hint is available, can we meaningfully and provably exploit it? That's the high level picture here. So this has been studied for the last, like I would say, 4 years almost. And I view this problem space as consisting of three prongs, or three gears, if you want to call it. You have metrics, you have resources, and you have hints. So what do we mean by that? So by metrics, I mean it can either be a comparative ratio for online algorithms, or it can be regret for machine learning style online optimization. And what are we trying to optimize, or what are we trying to save here? It could be resources. Maybe by using hints, I want to reduce the amount of memory I consume, or I want to cut down the number of iterations my algorithm runs, or I want to improve the overall running time of the algorithm. So those are the resources I want to improve by using the hints. And the hints themselves have various flavors. One could look at the type of hints that are provided. It could be just a bit, or it could be like a much more richer information. And one can look at what kind of errors the hints can incur. It could be like L1 or Hamming or other kinds of errors, or the size of the hints. It could be small or large, or even the type of the hints. What kind of hints are provided? And a most important question that we look at in this talk is number of uses of the hints. How many times does the algorithm have to use the hint in order to improve its performance? Okay. So to put these things into a concrete framework, I want to state three desiderata that we expect of any learning augmented framework. The first is consistency. And the question it asks is, how well does the algorithm perform when the hint is good? Okay. Suppose the hint is really good, it's very helpful. We want to study how well the algorithm performs. And what do we want? We want really near optimal performance or near offline performance when the hints are even reasonably good. So when the hints are pretty good, then we want like really good offline performance. It's almost as if the algorithm knows the future. But we also want a graceful degradation as the quality of the hints degrade. If the hints slowly become bad, we also want the algorithm to respond in a controlled manner. Almost a converse of this property is something we expect from the algorithm, which is robustness. There, we want to ask how well the algorithm performs when the hint is bad. We don't want the algorithm to give up saying that, oh, you gave me bad hints and so I'm allowed to do anything I want. Actually, we don't want that. In fact, we want the algorithm to degrade to a near online performance, even if the hints are very bad. In fact, even if the hints are adversarial, we want the algorithm to have a controlled error it makes. So we don't want, I mean, so for example, I could supply the hints to be in a noise, and we don't want the algorithm to be really bad. We want the algorithm to sort of fall back to a online performance. So these are not really complements of each other, but they are kind of strong requirements. And the third requirement that I want to add to this is parsimony. So what do I mean by that? The algorithm should use hints if they are useful. I should not ask for hints if it's not going to gain any benefit out of that. Okay. So at a stage in the performance, if the algorithm knows that by getting a hint it's not going to make any difference to that, it should not ask. Why? Because these days machine learning models tend to be more complicated, they are resource consuming, they are big, they're expensive to run, and so on. So we want to quantify this resource aspect of using the hints. So we want hints to be used only when they're required. Of course, this parsimony should not compromise on either consistency or robustness. And we want those two properties also to be retained, but we want, in addition, parsimony to be a property of the algorithm. And of course, all these things should work under no assumptions about the prediction error. The prediction can be, as I said, arbitrary. It could be like really good or really bad. You should not know much about how the prediction error is actually made. Okay. So that's the whole setup of learning augmented. So I'll give a very quick example just to uh, bring people into this frame of mind. The good example from classic algorithms is binary search. So we all know what this means. So we have a sorted array with say n elements. This array is A, and we have a query Q, and the goal is to find the index of this Q in this array if it exists. Assume it exists. And what do? We just compare this query to the middle of this array, and depending on which side, remember this array is sorted, so depending on which side the query falls, we recurse on the appropriate half of this array. Okay? And the number of probes this binary search makes is like log n to the base 2. So in a nice work, Lycouris and Vasilevsky considered this problem but with hints. So what do we mean by hints? The hint for this query, it gives you an idea of where this index could possibly occur. So in this case, the hint is given by h of q. It tells, here is where I think this index of this q will be there in this array. So here is the algorithm that can, following algorithm can use this hints. So what it does is it first compares this q with this hint, the location of the array with the hint. And of course, if you find the answer we're looking for, great. Otherwise, it'll do like a doubling trick, going in the direction where it obtains an interval within which the element q can possibly occur. So it probes a of this hint plus 2, hint plus 4, and so on, all these indices. And then until it finds this interval, which I've indicated in this yellow braces, and that's the interval where Q can possibly be. Okay? And then once it narrows down to the interval, it does a binary search on this interval. So that's is very simple algorithm. And to analyze the algorithm, notice that if epsilon is the error between the actual index T of Q and the supplied hint, then the number of probes is like 2 times log of epsilon, because the first log of epsilon is spent to first find this enclosing interval, and the second log of epsilon is to actually find Q within this narrowed down interval. And it's also very easy to see that this simple algorithm is both consistent and robust, because no matter how bad this the supplied hint is, you would never search more than like 2 log n probes. And if the supplied hint is really good, then you will narrow, the first step will run really fast, and then you'll be able to find it. So it's a nice simple algorithm. But this algorithm only uses one hint. In fact, this is not even an online problem, right? To truly speaking, it's just a offline, a data structure problem, right? But what we are interested in is to study these kinds of problems, but to control the number of hints that we want to supply. So as the first example, I will look at something called caching. I'm pretty sure most of you know the setup, but we will revisit this just for understanding the notation. Okay, this is a joint work with Sangjin, Aditya, and Manish. It appeared in this year, as you know. So in online caching, we have a sequence of pages, say P1, P2, P3 arriving online. And you have a cache of size K. It's a small cache. Think of K being small. And the goal is to keep pages in the cache such that when I request, when a new page arrives, you want that page to be in the cache. Otherwise, the algorithm is set to incur what is called a cache miss, and that costs that has a unit cost. Okay? So this is how the entire framework proceeds. For every time step, if the arriving page P sub T is not in the cache, then the algorithm has to assume the cache is full. The algorithm has to select a page in the cache to kick out. And since it has to bring PT into the cache, it incurs like a unit cost. And what we want to do is to minimize the total cost of this online algorithm. Right? Interestingly, the offline version of this problem was studied more than 50 years ago. And Bellady from IBM gave a very beautiful algorithm called furthest in the future. That, remember, this algorithm was almost like predates P. Right? This algorithm is optimum, and it's very simple. What it does is, remember, we know the entire future. So to understand who to kick out from the cache, we just look at all the times when the pages in the cache are going to arrive next, and pick the one that's going to arrive the latest and kick them out. Right? So it's a very simple rule. The key thing to notice here is that you don't need to know my entire arrival sequence. I just need to know when I'm going to arrive next. And that's actually a very interesting and important property. And this can be shown to be optimal, actually. And the objective of any online algorithms to remain C competitive against this offline optimum. So the expected cost should be at most C times the cost of this optimum. Okay. And in the hint setting, what we have is that identical framework, except just when the page PT arrives, it also comes with a hint, which is when am I going to come next. Okay. And the goal of the algorithm is to use this hint in any useful way, if possible, to improve the cache performance. So this notion of caching and hints was studied in a bunch of recent papers. Notice that if the hints have no errors, if the hints are perfect, then you can apply Bellady's rule, because Bellady, as I told you, don't need to know the entire future sequence. I just need to know when I'm going to show up next. So if the hints are perfect, then Bellady's rule is optimal. Lycouris and Vasilevsky extended this observation to work in the case when the hints have errors. Okay. And this result was improved further by Wei and Rothge. So their result is robust and consistent. That means if the algorithm is really good, the hints are super good, then you get great performance, and you don't get really bad performance if the hints are even adversely bad. However, the algorithm is not parsimonious. They have to query for every page when it's going to arrive next. Okay. What we do in this work is to study caching in the parsimonious setting. Right? And the assumption is that I can get a hint for any page in the cache, but I'm not going to ask for every page, but I'll selectively pick which ones I am going to ask hints for. And just to interpolate where this problem sits, if there are no queries allowed, then you get the classical online setting. And of course, if you're allowed query at every step, every time a page comes, I'm allowed to ask the hint when it's going to come next, then you fall back to the usual learning augmented setting. So it's kind of sits between these two settings. To understand our algorithms, I want to quickly recall uh, the family of algorithms that are almost a bread and butter of caching. They're called marking algorithms. It's like more like a framework. It's not, it's more like a mental experiment that helps analysis easier. And the algorithms proceed as follows. Uh, as time progresses, if the page that comes at time t is already in the cache, you mark it. Otherwise, if all the pages in the cache are marked, you unmark them. And then you evict an unmarked page. And then you fetch the incoming page and mark it. So basically, this algorithm proceeds in phases. And at the end of the phase, every page in the cache is marked. So you kind of start a new phase by unmarking everybody, and then you evict an unmarked page. So the only rule that's not specified here is evict. So that's the key to this algorithm. Who do I kick out from the cache? And in fact, in a very well-known result, Fiat et al. Showed that if I randomly pick a page from the cache, then this is log K competitive. So that already buys you a lot. Okay. So now what we'll do is we'll extend this simple eviction strategy to work with parsimonious hints. So first I'll present like a warm-up naive way of doing it. So here is the warm-up way. The rule is very simple. So let epsilon be some parameter that we choose. If at least epsilon fraction of the pages in the cache are unmarked, then you return a random unmarked page. Like you behave like the classic Fiat et al. Work. Otherwise, if the fraction of unmarked pages falls below epsilon, then for every unmarked page in the cache, fetch its arrival time. Ask the hint, get a hint for it when it's going to come next. Okay. Of course, we don't want to waste. If I've already asked a hint for a page, if it hasn't shown up, then I don't want to ask hint again because it's going to give me the same thing. So if you want to count in a very strict sense, right? So now what do I have for all the pages in the cache? I have the next arrival time given by the hint. Now I invoke Belady. So among these pages, I return the one that's going to appear furthest in the future, and that's the page I'm going to evict. So it's very simple. It's a simple like threshold based rule. Interestingly, you can show something slightly non-trivial with this already like simple rule, which is this algorithm uses epsilon times the length of sequence many hints, but gives you like a constant competitive ratio. Okay, assuming epsilon is constant. But you already see here a interesting trade-off between the number of times I query the hints oracle and the comparative ratio I can end up with. Right? And the proof idea is almost extending the classic like marking based analysis, except that we have to switch to a slightly different analysis until the fraction of the unmarked pages in the cache falls below epsilon. So it's like a simple generalization of the marking based analysis. Okay, so this gives some hope that you can do some things non-trivial even in the setting where you don't get hints at every time step. So you can do better than this. So this is an algorithm that we call adaptive. So what we do is that instead of waiting for the cache to fall below a certain range and then asking for hints, every time we get a cache miss, every time we need to evict somebody from the cache, we sample B unmarked pages from the cache without replacement. And for every page in the sample, you ask for the hint. So now we have B pages, all with hints, all with the future time when they're going to come next. And now apply Belady on the subset. Return the furthest in future among these sample pages. So it is more adaptive way of doing it. What we can show is that this algorithm can trade off. If the optimum number of cache misses is say below 1 over say k to the epsilon, then this algorithm will give a constant competitive ratio, but will make sublinear many queries, right? Because if it gets a certain competitive ratio, then we know that it every time it has a page miss, it invokes B times B many hints, and the number of page misses like competitive ratio times opt. So the number of hints it requires is B times the competitive ratio times the opt many queries. So under interesting settings, this number is sublinear in the sequence length. And how do we show this? It uses a notion, something called eviction chains, that was done in the original caching work of Lycurgus and Maslowitsky. Basically, an eviction chain is how does a given cache slot behave with respect to evictions. So basically, when pages are replaced by other pages, you track this chain of who replaces whom, and that is useful in order to understand how how the hints can play a role. So in a sense, you bound the expected length of the eviction chain. Of course, this proof tends to be easy when all the hints are good. In a sense, they are all like they don't have much errors. But if the hints do have errors, then you have to be a little more careful. You have to account things more carefully, and it becomes more and more delicate. Interestingly, this algorithm or this kind of bound is also tight, so we can get a lower bound. So the lower bound construction is fairly simple. Again, you assume k pages, and between phases you throw one page from the previous phase and include a new page, and then very specific way of constructing the lower bound gives rise to the following kind of guarantee that any C competitive algorithm has to make C times k to the 1 over C times opt many queries. Okay. So this is it's kind of very delicate, actually intricate analysis, because this is supposed to work for any kinds of algorithm. So you have to impose increasingly simplifying assumptions about the algorithm. You have to eliminate many kinds of weirdnesses they can do. So you have to narrow down to like a basic algorithm that has certain properties, and then analyze how many queries it should make in order to achieve this competitive ratio. Okay. So this, hopefully I've conveyed that even for a classical combinatorial setting, you can do away with asking hints at every time steps. You can get interesting non-trivial bounds even if you allow only sublinearly many hints. Okay. Yeah, any questions at this point? Okay. So now I'll switch gears and
You have
oh, sorry, go ahead please.
in the lower bound, when you put k c equal log k, you get log k, but it's actually 0. Yeah, I mean, if c is equal to k, then your theorem says omega of log k, but to get log k competitive, you don't need any query.
Yeah, which is correct, right? You don't need any query for log k competitive, right?
But your bound is log k.
Oh, so this is an omega tilde. It's not,
Omega tilde, sorry. Okay.
Yeah.
Didn't see the tilde. Thank you.
Yeah, I mean, this is like lower bound in the TCS sense. It's not tight up to log factors. Okay. Sorry, I cannot see the audience because my screen is all filled with my slides, so that's why I don't know if there are any questions. So, okay, so if you have questions, you can always ping me offline. So now I'll switch gears and do a different set of problems that can also benefit from sublinearly many hints. Okay, this is in the regret setting. So this work that we did with Aditya, Ashok, and Manish appeared last year in Europe. It's a linear optimization. I think most of you should be familiar with this, but this is should be more familiar to the people who are closer to ML, which is basically everybody these days. So the setup here is that you have assume that all actions take place in a unit ball and in d dimensions, like b sub d. Again, it's an online setting. At every time step, the algorithm is supposed to play a vector w, supposed to output a vector w. After it outputs a vector w, nature responds to this vector by outputting a vector cost vector c. And you compute the loss at this time step, which is the inner product of what the vector algorithm played, which is w, and what nature responded, which is c. And what we want to design an algorithm that that outputs w at every time step. And the goal is to minimize the regret. And the regret is defined as the difference between the loss of an algorithm and the loss of an ideal algorithm that responds a single vector, the same vector at every time step, which is w star. So you want to minimize this regret. So basically, if the algorithm knew the entire sequence, then, and if it's forced to respond only one vector every time step, then it will respond w star. And you want to measure our algorithm's performance against this class of benchmarks. And we call an algorithm to be good if it has a sublinear regret. And this was defined by the beautiful paper of Zinkovich two decades ago. Okay. And OLOs everywhere. It shows up in stochastic optimization when you want to train like ML models. It shows up in portfolio. In fact, there is a nice book of Elad Hazan that details like many applications of online linear optimization. It even has a role to play in like obtaining tight concentration inequalities in just probability. So just to give some background about what kind of tools we'll be using, so I'll just revisit FTL and FTRL quickly. So one of the very simple and intuitive algorithms, how would you play? Think about this. Like, how would I design an algorithm to play this WT, right? When I want to play. So one simple way I could do is that I know all the costs that have occurred in the past. I'll try to find out the W that's best against this cost. And I'll just play that, right? WT of FTL, that's the follow the leader. It's just playing the vector W that's the best for the past. Okay? So it's a greedy algorithm that's least loss over the previous rounds. Unfortunately, this alone is not enough. It can actually have linear regret. For example, you can even construct a simple example in the 1D where the signs are alternating, then this algorithm would have like a really terrible linear regret. But you can fix this easily by adding some kind of a regularizer. What you do is you incur the cost of this W and you add a regularizer term, and it turns out that this regularized follow the leader FTRL can be shown to have like a sublinear regret. Basically, this algorithm is good. So that's something to keep in mind. And in fact, FTRL and both FTL and FTRL also satisfy another nice properties, which is if the some of the costs are linear and the costs are linearly growing, right? Then you can show that the FTL already achieves a log regret. So the bad situation happens only when the costs are actually small, right? If the costs are linearly growing, then all things are good. Something to keep in mind. And you can extend this simple observation even to FTRL. So get the same result. Okay, this is the background we need for online linear optimization. Okay, so what is our setting? We'll study the same problem, online linear optimization, but with hints. So before the algorithm plays W, it has access to a hint vector HT. And hopefully it can use this hint vector to decide what W it's going to play next. But the rest of the notion stays the same. The loss at every step, the notion of regret, everything stays the same. But we want the algorithm to gainfully use the hint to do better. And when is a hint good? We need that notion as well, right? We call a hint to be good if it's alpha correlated with the cost that is yet to appear, right? A hint HT appears before nature provides a cost. But we want to call the hint to be good if it's reasonably correlated with the cost. So pictorially, it looks something like that. We have this cost, red, which is unknown. All the stuff above this hyperplane are good hints, and the ones below them are bad hints. Okay? And we also want to define what is the query cost of a hint. We choose this particular definition. We say that the query cost of a hint is alpha times the length of the vector C, regardless of its quality. Okay? So we don't care whether the hint is good or bad. We just prescribe this cost whenever you ask for the hint. Okay, so this problem has been studied in the past in like various disguises. So remember, like sublinear regret bounds are good because sublinear means the average performance approaches like a fixed benchmark over time. So of course, the classical regret bounds are sublinear and they're tight. So Hazan and Megiddo many years ago studied the following special setting. If the first, say the first coordinate of the cost is known, and if it is sufficiently contributing to the cost vector, basically its magnitude is more than alpha, then you can actually get logarithmic regret. So you can get regret something like d squared log t over this correlation alpha. So that's quite interesting, right? Because you know something very, very minimal about the cost, but already can go from root t to log t. Okay? In some sense, this result was made stronger in a more recent work by Deckel et al., where they showed that you don't need to know the first coordinate exactly. But as long as every hint is alpha correlated with the cost, then that's enough to assure that the regret, I get to say d log t over alpha. Okay. So this result is consistent, but not robust, not parsimonious. So they do require that every hint is good or alpha correlated, and they do need hint for every time step. Okay. So when we considered this problem like a couple of years ago, we in a sense made this result robust. So we showed that even if most hints are alpha correlated, then you can get regret bound. In fact, we get rid of the dimension dependence in the regret bound. So we get log t regret. So our result was consistent, robust, but not parsimonious. We still require hints at every time step. So that's the history of this problem. What we show in this paper is the following result. If there are B bad hints, bad is when the hints are not alpha correlated with the cost, then we get an algorithm whose regret is root B log t over alpha. Okay. So let's stare at this bound for a minute. First, look at consistency. When the hints are all good, when B is 0, there are no bad hints, then this regret bound is automatically log t over alpha. And at the other extreme, when every hint is bad, that means B is t, even then, I dropped the log t, but you can actually get a tighter bound. You can show that the regret is still a square root t. It doesn't go really bad. And this algorithm, we also show that the expected query cost is order root t. So what we obtained is that a robust, consistent algorithm that is also parsimonious, basically sublinear number of hints. Okay. And what is the key idea here? So the main observation here is that how to use the hint. Okay. So let's assume for simplicity that all the hints are good. Okay. There are two cases. The first case is when FTRL fails, when the follow the regularis leader, in this case the yellow vector, gives me something that is not well correlated with the cost that's going to appear next. So if I use FTRL, it'll be really bad. It's going to have a huge regret. In this case, I want to use hints because hints are very well correlated. Okay. If FTRL is unable to predict CT, then I want to use a hint. And that's good because I can decrease a regret. Hint is correlated by factor alpha. So I can decrease a regret by another factor alpha by using by expending query of cost alpha. So if I spend like order root t query cost, I can completely cancel the FTRL regret, which is FTR square root t. Basically, I'll be back to almost zero regret or log t regret. Right? That's actually a case when FTRL doesn't work. But what about when FTRL actually is good? When FTRL gives you a vector that's actually well correlated with the cost, it might be a bad idea to use a hint. Actually, using a hint can actually might hurt. But how do we control the regret in this case? That's the key point. And here is how the entire proof kind of works. The first case is when FTRL doesn't work, where every hint I invoke subtracts some amount from the regret, from the FTRL regret. So I need like square root t queries. And the second case, when FTRL does really good, what we show is that if that means the length of the cost vectors is actually linear, which we already saw that that's enough to guarantee that FTRL will give you log regret. So that's the other case. So it's an easy case for FTRL without any hints, right? So the main question is, how do we detect which two cases I am in? Because the algorithm doesn't know whether it's in case 1 or case 2. And the main idea is to use a hint chooser, some kind of a mechanism, which itself is like an online gradient descent, a one-dimensional version of the problem, which decides when to use a hint. So it has a controlling probability PT. It tosses a coin with probability PT. If it turns out to be heads, then it uses the hints. If it turns out to be tails, uses FTRL. And it computes a loss in a certain way, basically, which combines both these things, loss of using the hint as well as loss of using FTRL, and sends the losses to both these algorithms to update them. So the hint probability kind of gets updated every step. So if FTRL keeps going fine, you never use a hint. But if FTRL starts misbehaving, then you start using the hint. Yeah. So it turns out that this, just to recap, so that's the basic algorithm. So I'll just, given that I only have a couple of minutes, I'll wrap it up. So recall, this is the upper bound. And it turns out that pretty much every term in this bound is tight. So the root b log t 1 over alpha is tight. The number of queries has to be square root t. And in fact, you also need randomization. You can show that any deterministic algorithm with log regret will use t over log t hints. Cannot get sublinear many hints. So I'll skip the lower bound, one example lower bound. I want to conclude with the summary. So we saw two examples where learning augmented algorithms were designed to be parsimonious. So they did not require hints at every time step. They required, in fact, in both cases, and under certain settings, sublinearly many hints. So I feel that this opens up a rich set of algorithmic questions. How do you take this learning augmented framework and make it more resource conscious and resource efficient? And of course, one of the things that I'm always interested in is practical applications. It'd be nice if these kinds of algorithms actually get used in practice and you can see the benefits. And for the complexity theorists in the audience, I always end with a plugin that we should also be defining some class like P to the ML that brings the benefits of machine learning to more fundamental problems in computer science and complexity. Thank you very much.
Are there any questions? So if there are no other, there is one question.
Hi, thanks for the nice talk. So I just wondering, this notion of errors that you have. I guess you can probably enhance your results if you haven't already done so by just some use of, this is the expected number of errors or things like that. That's probably a more realistic setting, right?
Sorry, restricted number of errors? Like, what do you mean by that?
Restricting the number of, have some kind of bounds on the errors in terms of, expectation or something like that.
So remember that the algorithm doesn't assume how the predictions are behaving. So they are oblivious to that aspect. So
if you do take advantage of that, can you take advantage of that? But if I say that, saying that there are B errors,
Yeah. So the bound will reflect, right, how well the prediction errors are. Like, the advantage is reflected in the bound, not in the algorithm. We are asking whether the algorithm can take advantage of that. It's possible, but we didn't, it'll make it like, less uniform in some sense. Yeah.
thanks.
Any other questions for Ravi? Yes, so if there are no other questions, let's thank Ravi again.
Thank you.